Have you ever stopped to think about how far you've actually traveled? I mean, it sounds like a super simple question, right? But in physics, the answer can be, well, it can be way more complex than you think. Today, we're going to break down two totally different ways to measure movement that'll pretty much change how you look at getting from point A to point B. Let's get into it. So, let's start with the story. Picture a hiker, okay? They're out deep in the woods. They want to get from their camp to this cool landmark, but the path is anything but straight. They've got to weave around trees, scramble up these muddy slopes, and follow trails that twist and turn. They can't just, point and walk. That's just not how it works out there. And this right here, this brings us to the central puzzle. Our hiker is putting in a ton of effort, right? Covering a lot of ground. But at the end of the day, they might only be a short walk from their tent. So, how far did they really go? Well, it turns out there are two completely different and equally correct answers to that question. All right, let's tackle that first answer. This is the one that probably feels the most natural to all of us. It's all about the total journey, every single step you took along the way. This is what we call distance. Just think of it as the complete total length of the path you travel. It's the full, detailed story of your journey. And this is key. It doesn't care one bit about direction. All that matters is the total ground you covered. The absolute best way to think about distance is your car's odometer. Seriously, it doesn't matter if you're driving forward, if you have to back up, or if you're just driving in circles looking for parking. That number just keeps on ticking up, tracking every single meter you travel. So for our hiker, after all that scrambling and following that winding path, the total distance they traveled was a whopping 2,800 meters. That's the number their fitness tracker would be buzzing about for sure. But what if we don't really care about the path they took? What if all we care about is the end result? Where did they end up compared to where they started? This brings us to our second and very different way of measuring movement. And this is displacement. Displacement is the overall change in where you are. It's the straight line path, as the crow flies, from your starting point to your ending point. And here's the crucial part. It always includes a direction. So let's go back to our hiker. Even though they walked 2,800 meters, their final position was only 1,400 meters northwest of where they started. Get this, the distance they traveled was literally double their displacement. And this is where physics starts to get really, really cool. So we've got two totally different numbers describing the exact same trip. To really get why, we need to dig into the fundamental principle that actually separates them. And that brings us to the core scientific concept here, scalar versus vector. Distance is a scalar. All that means is it only has a magnitude, a size, a number. It just answers the question, how much? But displacement is a vector. It has both magnitude and direction. It answers how much and which way. Okay, let's just quickly break down what this means in the real world. Distance, it depends on every twist and turn you take. It's always a positive number, and it gives you the full story of your journey. Displacement, on the other hand, only cares about where you start and where you end. It can be positive, negative, or even zero, and it just gives you the net result of your trip. Let's look at another quick example. Imagine a car drives 100 meters forward, then has to back up 50 meters. The distance, just like that odometer, adds it all up. 100 plus 50 is 150 meters. Simple enough. But the displacement, well, the car only ended up 50 meters from where it started. Its overall change in position is just 50 meters. See the difference? Okay, pop quiz time. An Olympic runner completes one perfect 400-meter lap around the track. Their distance is obviously 400 meters, but what is their displacement? Think about it for a second. The answer is 0. This is the perfect example. Their distance is 400 meters, a massive effort. But because their final position is the exact same as their starting position, their displacement, their overall change in position, is 0. From a physics standpoint, it's like they never moved at all. And this stuff applies to everyday life all the time. You might leave your house, drive 4.3 miles to the store, and then drive another 6.4 miles to a friend's house. Your odometer says you've gone 10.7 miles. That's your distance. But if your friend only lives 2.1 miles from your house as the crow flies, well, that's your final displacement. So we know displacement is the straight line path. But how do we actually find that path when the movement isn't just a simple line back and forth? How do scientists and engineers actually calculate that shortcut? Well, this is where a little bit of high school geometry comes back to save the day, the Pythagorean theorem.
If you move, say, 4 meters in one direction and 3 meters in a direction perpendicular to that, we can use this handy little formula to find the direct path between the start and end. As you can see, the math gives us a straight line shortcut of exactly 5 meters. Then you just add a direction, and boom, you've got your displacement vector. Okay, so we've got distance, the long, winding path, and displacement, the direct shortcut. So why do we need both? I mean, why isn't one just better than the other? The big takeaway here is that they're two different tools for two completely different jobs. Distance is perfect for measuring total effort. It tells you how much fuel your car used, how many calories you burned on a hike, or the wear and tear on your running shoes. But displacement, that's essential for navigation. Your GPS doesn't care about the scenic route you took yesterday. It needs to calculate your displacement from your destination to find the most direct path forward. This isn't just a neat party trick. It's the foundation for understanding everything from velocity to how a self-driving car gets around town.
And that brings us to a final thought to leave you with. Your commute to work and back might cover 30 miles of distance every single day. But since you start and end at home, your total displacement for that whole journey is 0. So from a pure physics perspective, did you really go anywhere at all? It's something to think about on your next drive home.